Welcome everyone to lecture 5. In this video we want to talk about the Monte Carlo method, as you can see. Like last week, I prepared a few slides so that we can quickly skim through the material so that the videos will be shorter and it's more like a summary of the lecture notes. And yeah, so this will be the format like last time. Last time you also saw another dinosaur plot, and for some strange reason I find this quite soothing to create. So here is another one. Maybe I will do more in the future, or hide them in the middle of the video so that you're forced to find them. In any case, let's talk about the real material we deal with in this week, which starts with the strong law of large numbers. That's a classic theorem from elementary probability theory, and basically says that the average of IID random variables converges to the mean of said random variables, if that mean actually exists. I mean, if it doesn't exist, there's nothing to converge to. But in any case, that's a really important result from probability theory. And in terms of Monte Carlo simulations, this is like the fundamental theory behind Monte Carlo simulation, because it says nothing else than if you do stuff or do random experiments often enough and average the results, then you will converge to the you will basically approximate the true mean if you do it often enough. And here, if you, for instance, instead of using random variables, if you still use random variables, but instead of using arbitrary random variables, if you use, for instance, a random indicator function with some event in there, in that indicator function, then this average will converge to the probability that this specific event you were looking at actually occurs. And so this is what Monte Carlo method is about. It's about repeating an experiment often enough so that we can approximate the probability we want to estimate, or the value, the mean value we want to estimate, through repetition and averaging. And basically the Monte Carlo method is letting the computer do all this repeating and this simulation of experiments. So how do we simulate an experiment? Basically it's nothing else than generating random numbers that correspond to that experiment. Remember that from probability theory, that a random variable is nothing else than the summary of a random experiment. So therefore we generate enough outcomes or summaries of random experiments that correspond to what we want to look at. For instance, in the lecture notes I had this example here. So a buddy of mine, Lars, and I want to meet at a bar. I mean, in theory, currently it's not possible due to COVID. But in general, if we want to meet at a predetermined bar in the city, and we are thinking about meeting between 3 and 4, but don't specify when we will meet exactly. So everyone just shows up at a random time between 3 p.m. and 4 p.m. So each one of us has an arrival time that could be coded as something between 0 and 60. So as a random point in time between 0 and 60 minutes, like 60 minutes in an hour. And if we simulate random arrival times, both for me and for Lars, then we will get independently scattered points within this cube here, or in this square here, in the square from 0 to 60 on both axes. But the point is that Lars and I won't wait indefinitely for each other. So each one of us won't show up before 3 p.m, but will also not wait longer than 4 p.m. And also we will only wait like 15 minutes until we leave again. So this makes it a bit tricky. So our meeting won't occur definitely. It will only occur if we show up within 15 minutes of each other. So this means that the randomly scattered points need to fall within this blue area, so that this represents that the event that the meeting occurs. So this is how you would translate an experiment into random variables that you can simulate then. And then it's really straightforward. You simply or determine how many times you want to simulate your experiment. Recall that if you average over enough experiments, then you get close to the true value, so you need to simulate the experiment often enough. So here typically you take just a large number, say in this case it's 100, no, it's actually 1 million. And then for both me and Lars, you will generate the not standard, but uniform random variables that are between 0 and 60. And then you will simply check, okay, is the difference between the two arrival times less than 15? And you simply count how many times it occurred and divide by the amount of experiments you ran. And in this way, you can approximate the true probability. In the lecture notes, I compared this to the theoretical value. It's pretty straightforward to compute the theoretical value, and I think it came quite close to it. In any case, if we were to increase our number of experiments, we could get arbitrarily close to the real probability. And of course, in this kind of case, it doesn't really make sense to simulate, or it's not that useful because you already have a theoretical quantity or a theoretical probability you can compute. It makes more sense when things are not as nice as in this scenario where everything is independent of each other. And one particular area where this is true, so where independence is false and dependence is true, is with stochastic processes. So here, for instance, you can look at the Poisson process. The formula of how it is defined is in the lecture notes, but here you only want to give the intuition behind the Poisson process. So in this case, we have something which is time dependent, because as you can see, this variable n, it increases with time. So this is fundamentally already shows some time dependence, because things cannot randomly go up or down or whatever. You know, you can only stay at the same level or jump by one step. What is random here in this case with the Poisson process is that the waiting times where you stay on one level is exponentially distributed, and all of these waiting times in one levels are independent of each other, and this will generate a sequence if you sum them up and jump by one whenever one of your waiting times is up. Then you will generate a sequence like this, which will resemble, or which will be what is called the Poisson process. Often you can think about this as the number of customers that are being served, for instance, or the number of claims that an insurer has to pay. So these are typical applications of the Poisson process. For instance, if you'd say that after t is equal to 5, so let's say after 5 minutes we have served 2 customers. And the point of this is that it's not that easy to get the probability distribution at each time point. So here we have at each time point we have one random variable, and this is what a stochastic process then ends up to be. So a stochastic process is nothing but a collection of random variables. So for each time point we have one random variable, and the distribution of of the random variable at one time point is not always easy to determine, because, for instance, if you look at time point t, then you will need to know the waiting times before that. And so the more you go along the time axis, the more other random variables you have to consider, and these might be dependent or not. So this is where the dependence makes things a little bit harder. And this is basically the Poisson process. In this case, it's just a process that can waits in a random exponential time and then jumps by 1. And as I said, this is often used, for instance, in insurance, where the number of claims that an insurer has to pay is modeled via a Poisson process. And if you then have also, so here n, what we have here is a Poisson process where lambda is the rate of the exponential waiting times. If you have that, then you can also use it to compute something which is called a compound Poisson process, which is nothing else than a sum of a random sum where the amount of terms you want to add is random and determined by a Poisson process, and the terms that you add up are also random variables. So in this case, in the insurance setting, it would be in the claim amount. There's a random amount of time until something happens, like I don't know, a storm or whatever, so that there comes a new claim for the insurer, and then the damage or the damage of the storm would be the height of the claim, and this would be then my psi in this case or in this scenario. So basically this whole sum is a random variable and determines how much an insurer has to pay at a specific point in time. And of course this will have to be compensated by the initial amount of money that the insurer has anyway, and the money that it gets from its customers as part of their contract over time. So in general, insurer will need to have this to be larger than the amount it has to pay. Otherwise, it will go bankrupt. That's, I think, pretty easy to understand. And this is called the Kramer-Lundberg model. So this is using this compound Poisson process and assuming an initial amount of money and a constant influx of money from the customers is a popular model. In this case, it's called the Kramer-Lundberg model. And we don't actually have to understand a lot of theoretical properties of this model or of the compound Poisson process. We can simply simulate this part here and then check how often does the sum here go below zero, and then count how many times that happens and divide this by the amount of trials we ran or how many scenarios we considered, and then we'll get an estimate of the ruin probability. So here is so what we want to do is to estimate a 10-year ruin probability under the assumption that the claims an insurer has to pay are all IID random variables and follow an exponential distribution. And here are a couple of initial parameters. So the initial amount of cash is just 0.25. You can scale it by whatever number you want. If you want to think about an insurer having more money, so you could multiply this by 2 million or whatever, if the numbers feel more realistic to you. I simply stuck to easy numbers. The constant amount of money an insurer gets is determined by C. In this case, it's just taken as 1. And then the parameters of both the waiting times of the Poisson process and the intensity of the claims. So this parameter here are given here. And then, of course, we need to determine how many times we want to simulate this. In this case, 10,000 times. And of course, we want to look over a time period of 10 years, because this is what we need to consider if we want to estimate the 10-year ruin probability. So it's pretty straightforward. As I said, we only need to simulate enough processes and then compute the sum. So the cash I have at time point t minus the amount of claims I had to pay until time t, and check if at some point during our time from 0 to 10 this will go below 0. And if it happens, then of course a ruin occurred, and then we can increase our counter of ruined our ruin counter by 1. So here I created an empty vector that will for each scenario will save whether a ruin occurred or not. And then for each scenario we simply start with x as our initial amount of money. At this point we don't have a ruin, so we set this to false. and we're currently at time 0. In each scenario, it always starts the same. And then we simply simulate until we're beyond the time horizon. So we simulate the waiting time between the next or between two claims that occur. We know that the claim, if it occurs, will be something which is exponentially distributed. So we simulate an exponential distribution, and then we simply increase our time by t, and we check whether our previous amount of cash we held plus what we get in the meantime during the waiting is less than what we had to pay later on. So we check, basically say compute this way how much money we have now, and we check, well, is this less than 0? If so, then we set our ruin counter to true and break out of the while loop, and then save whether a ruin occurred or not. So if it occurred, we would break out of the while loop, and then we will set this to true. In the other case, we'll never break out of the while loop until we are beyond our time horizon, and then we'll of course set this to false because no ruin occurred. And then we simply have to compute the mean of the ruin occurred. This is basically because true or false vectors can be translated to zeros and ones, and then of course the mean is nothing but an estimate of the probability. So here we estimated that the 10-year ruin probability with those initial parameters is approximately 51%, so that's quite high. So either the insurer will need to get more initial cash from somewhere, or need to ask their customers to pay more, or figure something else out. In any case, it's quite a high probability, and here Monte Carlo methods help to estimate this. So this is how you simulate a Poisson process or a compound Poisson process, and that's how you use it for applications like ruin theory. What you also often look at are not processes that make jumps. So the Poisson process made a jump by 1, and then the next time also again by 1, and the compound Poisson process makes jumps, but not by 1, but a random amount, could be positive, could be negative. So it will always have jumps, or the processes we looked at will always have jumps. Another process we can consider is the Brownian motion, or also called Wiener Process, which is something a bit different because it has continuous paths, so it doesn't make jumps. So it is defined as starting at 0 and being continuous in every path. And what's also true is that it has independent increments, which basically means that if we look at the difference of two random variables, or at the differences of the process at two different points in time, this difference will always be independent of any value before that, at any previous value. So of course this is a random variable and this is a random variable, and these two random variables are independent then. So this is something which is quite useful in simulation. We'll see in a few seconds why this is useful. And what is also true for this particular process is that the differences, these increments, are randomly distributed with mean 0 and variance equal to the time difference between those 2 points. And why is this a nice process? Or why can we simulate this process quite nicely? Well, it turns out that if you just want to compute the process over time, you can do it iteratively. You know the starting value is always 0, and then you can go to the next time step by decomposing your process into this difference plus what you added in here. So this is basically 0 here, so you change nothing, but you know now that this difference is independent of this. And by the normality assumption, you know that this is normally distributed, and therefore, since we can't simulate normal distributions, all we have to do is take our previous value and add to it a normal variable with appropriate variance. So in this case, again, the time between those 2 points. If you want to use a standard normal distribution, you can simply take out the variance by using the square root here, and this will be just simply the alternative. So this is in distribution the same as this, and otherwise it's still the same. So therefore we can iteratively simulate the Wiener process, and this may look like something like this. And as you can see here, it's continuous. It doesn't have any jumps, even though it can look quite rough. So it's not really, it doesn't need to be smooth, but still it cannot make jumps. And this process is often converted to another stochastic process, namely the geometric Brownian motion, by simply using this formula here. So here mu, sigma square, mu and sigma square and S0 are parameters. So S0 is basically the initial value of my process S, and mu is called the drift parameter, and sigma is called the volatility. And if we have simulated a Brownian motion as we just did in the previous picture, then we can simply take those values, multiply them by sigma, and then do the rest of the calculation here. So there's nothing really magical happening here. It's a straightforward computation. Here, if you already have the time scale and the realization of the Brownian motion from before, then you simply transform it in one line. And then if you do that, you get a different process. This is quite intuitive, I think. You simply take, or it's easy, you take a Brownian motion, throw it into the formula, and then you get a geometric Brownian motion. So why is this interesting? Well, the geometric Brownian motion is often used in the so-called BlackScholes model, which is a theoretical model to try to approximate market behavior. So it's basically a market model. So the BlackScholes model in its is quite simple. It assumes that the market consists of two assets, one risk-free asset, so basically your bank account where you can put money and get a constant return, which we denote by R, or a risky asset, so a stock. And the stock price will be determined by the geometric Brownian motion. So this is the standard setting of the BlackScholes model, and this is also why the geometric Brownian motion is so popular, because the BlackScholes model is popular, and this is because the BlackScholes model can be used to theoretically price different assets. And here we don't want to do it theoretically, although I will show you the formula for one specific asset, but it's also used, the BlackScholes model is also popular because we can simulate this geometric Brownian motion quite easily, as we've just seen, and then we can price assets by simply simulating the resulting cash flows. What do I mean by this? Think about a call option. For those of you who don't know, a call option is basically a financial instrument that allows the buyer of said option to buy the stock. In this case, there's only one stock in this market model, to buy it at a predetermined time. At a predetermined time at a specific price K. So this means if the stock price is has risen quite a lot, and your strike price is low, you can buy it for the cheap price, the strike price, because the option gave you the right to do so, and then you can immediately sell the option again at the current market value, and therefore generate a profit. It's basically a nice tool to gamble if you want to bet on a stock price, if it will go up or down. So the cash flow that results at the end time t, at the predetermined time t, is basically the stock price minus the strike price. so the difference of that, or it is 0, because you don't have to exercise the option. And of course, if you can get the stock cheaper at the market value, why would you pay more than you'll have to? So in that case, the option would be worthless. So this is a cash flow that comes from this kind of financial instrument, and the question then becomes, okay, how much do I have to pay for such an option? And the trick to determine is basically simulating the resulting stock prices, and from that you can simulate the resulting cash flow of the option, and then you can check, okay, on average, how much money will I generate with this call option, and this is then used as the price or the fair price for this option. That's basically the idea. In theory, as I said, in the BlackScholes model, there is a neat formula to compute this theoretically. Here in this case, you can compute the price of the option at time t via this formula. It looks a bit intimidating if you haven't seen it before, but basically this is the CDF of a normal distribution. This is the stock price at time t. This is the CDF again. This is the strike price. And this is basically the discounting value. Because if things happen in the future, you will need to bring that back to the present value by discounting with the risk-free interest rate. So that's basically this. And these two values are denoted here. You don't have to understand anything about this or why they look the way that they look. It's just a theoretical value, and I want to use it for comparison with my Monte Carlo simulation, because this is what we want to do here. So for the Monte Carlo simulation, we will need initial parameters again. So we will have the volatility of the stock price here. We have the initial stock price value. Then we will look at the time horizon. In this case, we will again look at the 10-year time horizon. Also, we will have the risk-free interest rate at 2%, the strike price that is predetermined. And then we will look at 10,000 scenarios again. As I said, with that we can easily compute the theoretical price, because basically I just define all the quantities that are present in this formula here. And with that, I can compute D1 and D2, and then simply plug it into the CDF function for the normal distribution and evaluate the formula. So right now I want to estimate or compute the option at time 0, so the value of the option today, if I want to get the right to buy the stock in 10 years. So this is what I want to do. So this is why we have here, we multiply by the time horizon instead of a difference here, because we're currently at time 0, so this is why this here is simply equal to 0. Alright, let's talk about the more interesting part about the Monte Carlo simulation. So here, again, we will need to have a vector that saves the payoffs that we simulate for each scenario. And then it's super easy. You generate geometric Brownian motions with appropriate parameters. In this case, you will need to choose the drift as being equal to the risk-free interest rate in this market model. This has some reasons that you would learn in financial mathematics. If this drift parameter is equal to the risk-free interest rate, it means that we look at something which is called a risk-neutral measure. I don't want to go into details here. Basically just know we will need this if we want to generate the appropriate stochastic processes or the appropriate geometric Brownian motions for the pricing, and the pricing needs this risk neutrality. In any case, it's pretty straightforward. If you have a function that generates geometric Brownian motions for you, that's what you will do in the or define in the exercises. So you will need to compute this on your own. And once you have that, you simply compute the payoff by the formula we looked at earlier. So this is the stock price at the end of the period, and this is the strike price. So therefore you only need to compute the maximum. And this way you get a payoff at each for each scenario, so for each path of the stock price, and then you can simply compute the mean, and then you have to discount it to the present value, because basically if you put money into the bank, for those of you who know what discounting is, it's you can ignore this explanation. But for those of you who don't, basically if you put money into the bank today, you get interest, and you kind of have to compensate with this interest when you look at future payments, because you will need to take into account that you could have gotten interest if you just put your money into your bank. And this is why you need to take the value in the future and do the inverse of getting interest, and this is what we call discounting. So basically this is the formula to do this, and once we have that, then we can compare the theoretical value by our Monte Carlo value, and we see that again it comes quite close to the real theoretical value. And this is another sign of how easy it is to simulate with Monte Carlo methods, and how easy it is to compute quantities even though you do not understand the all theoretical parts of a stochastic process. Because sometimes it's really complicated to know the theoretical properties of a stochastic process, depending on how complicated the dependence structure of this process is. But with simulations, you can simply simulate a path, and then in that path use these numbers to compute the cash flow you want to generate. And this way you can then simply run enough scenarios and average over all of these to compute an estimate of the theoretical quantity. All right. So that's everything I want to say about our lectures or lecture notes. But as last time, I kind of want to talk about the exercises too. So let's look at the exercises. Most of them are pretty straightforward. So in the first exercise, you will need to simulate the Poisson process. So you will write a function which I call simulate PP. So simulate Poisson process. And basically what you will do is you will simulate the Poisson process on a time grid, like so. The output, how it at the end is supposed to look like, is given here. And what I want to see at the end is that for each time value, so the Poisson process evaluated at each time point from t equal to 0 to t is equal to 10, I want to see how that is distributed, and I want to compare that to the theoretical mean value that is given here. Also, since we haven't covered yet how to collect whole processes in a for loop, you can iteratively extend the tibble, even though that's not the fastest way to do it. In this case, it should still work. And we will learn with lists later on how we can do it more efficiently. Then you will, in the second exercise, will consider ruin theory again. So you'll need to consider the Kramer-Lundberg model again. And basically you can use the code from the lecture. But what you want to do as well is that you exchange the distribution of the claims. So in the lecture we used exponential distribution. You simply write a function that can use other distributions too. So a geometric distribution, or a Poisson distribution, or a chi-square distribution. And you will need to figure out how to code this into a function so that the function knows which distribution to use. The third exercise is basically straightforward. Implement the geometric Brownian motion simulation. As I already said, this is what you will have to do in this exercise, and this is the part I left out in the Monte Carlo simulation of the BlackScholes model. And the last exercise is maybe a bit tricky, so this is why I want to give you a couple of hints. So a Gaussian process is a huge class of processes for which each finite dimensional distribution follows a multivariate normal distribution. So what does that mean? A process, as I've already said before, is a collection of a lot of random variables. And you can always pick a few random variables in here. So for instance, at time t1, t2, t3, and look at them into a vector. Look at all 3 points simultaneously. And this way you will get a vector, random vector. And the point of a Gaussian process is that all of these vectors, doesn't matter how many points you look at simultaneously, or what specific time point you look at, all of these vectors will follow a multivariate normal distribution. That's the point of a Gaussian process. And the beauty of a Gaussian process is that it can be completely described by its mean function. So it's the expected value of the process at each time point, and by its covariance function, which is the covariance between 2 time points. You don't need more than that to characterize the Gaussian process. So in this exercise, I want you to simulate a Gaussian process on a grid from 0 to 5 with a specific mean function and a specific covariance function. And the idea behind that is that you simply need to simulate one multivariate normal distribution, which has the length of corresponding to all of these values. That is because if you have a multivariate normal distribution with appropriate mean vector and covariance matrix, so n here is the amount that would correspond to all points in our time grids. This is what you will need to simulate, and what makes the multivariate normal distribution nice is that if you pick out a few components of that vector, you will simply need to take the appropriate values from the mean vector and the appropriate values from the covariance matrix, and then you already have everything you need to describe the multivariate normal distribution of this smaller resulting vector. It's written in Wikipedia quite nicely. If you want to look at it again, basically if you have a 3-dimensional multivariate normal distributed vector with mean vector like this and a covariance matrix, and if you only want to look at the first and third component, as in here, then this vector is multivariately normal distributed again, with the mean vector corresponding to the mean of the first and third component, and the covariance matrix is basically the result of throwing out all values that correspond or that deal with the second component. So that's quite easy, and the multivariate normal distribution is quite nice this way, and therefore you will only need to simulate one realization of one multivariate normal distribution that has appropriate length and appropriate parameters as depicted here. So that's a bit tricky, that's why I wanted to give you a couple of hints on that, and I think, or I hope, with that you should be able to simulate that as well, even though we haven't covered Gaussian processes in that much detail. Yeah, so that's it, that's all I wanted to cover. Alright then see you next week, bye.